So good morning, everyone, for joining for our webinar series. And this is the series which we started. This is our inaugural session, to be honest, and we are going to start this for we are going to continue this as a bi-weekly webinar series, and we are going to invite experts in the area of geotechnical engineering, structure, uh, transportation, environment engineering, water resources. So we are going to cover mostly everything in this series. And every alternate week, we will have one speaker from a one specialization. So that way, we are planning to cover at least two speakers from each specialization every semester. So this is just a start of the semester, and I'm really thankful to Dr. Biswas for agreeing to give the inaugural first session on this webinar series. And I'm sure this is going to be very enlightened session for everyone. It's like my honor, to be honest, to introduce Dr. Vishwas with everyone. He is a very dear friend of mine. Recently joined as an assistant professor in Department of Civil Engineering, UMass Lowell, and before that, he was working as a senior research engineer as well as a postdoctoral engineer researcher at Texas A&M University. Currently, he majorly focused towards developing the advanced method for the health monitoring of the geotechnical infrastructure and water returning infrastructure using drones, robots, satellites data, and application of artificial intelligence and machine learning. Dr. Vishwas have worked advanced ground improvement technologies, application of geosynthetic in transportation infrastructure, and development of the sustainable and resilient solution using low carbon material. I'm happy to share that he also joined recently as a standing committee member of AKG 80 and TRB, and he is also serving as a ASC member of Sustainability and Geotechnical Engineering, which is like a prestigious association, and having a standing committee membership in the TRB is a really a big thing. So I congratulate Dr. Vishwas for this. And now I invite Dr. Vishwas to deliver a webinar on role of Wicking Geotextile for improving the resiliency of the pavement infrastructure, forum and laboratory to practice. Thank you. Dr. Vishwas, over to you.
Uh, Thank you so much, Nitin, for the invitation, and I'm glad to be the inaugural presenter for your webinar series. So I will then start sharing my screen.
Yes.
I will just need a confirmation, like if you can just confirm if you can see
Yeah.
the screen.
Yes, we can see your screen. We can see your presentation. And
And
now it's in presentation mode.
okay, all right,
Okay. You're good. Thank you.
all right. Thank you again. Yeah. So thank you everyone for planning to attend this webinar series. So in this one, I plan to talk about the role of Wicking Geotextiles for improving resiliency in pavement infrastructure from laboratory to practice. So this is the work which I essentially started when I was starting my PhD in Texas, and I learned a lot on this work over the period of my PhD, and then I also worked with this material in my postdoctoral role, and we are also doing something more. Right now, also a couple of my colleagues are working on this geotextile. So I will try to share something which we have learned together on this particular geotextile. So moving to the next slide. So none of these works were done alone individually. It is a group effort. So I would like to acknowledge everyone who has helped me or supported me during the course of this work in both different institutes like Texas A&M, Michigan, Fugro, and also the agencies who have essentially supported this research like Solmax, TexDOT, Minnesota Roads, as well as the NSF Foundation, NSF IOCRC. So thank you again. So with that, so this will be a short outline. So I will just have a quick introduction, and then I will directly jump into two case studies. The first one essentially is like what we studied on use of these geotextiles in Texas, and the other one is how we use this geotextile in Minnesota. But both of these projects are related to pavement infrastructure because that was the principal focus. And then I will just quickly show you some ongoing efforts, what we are still trying to do, and then I will conclude with some summary comments. So to keep a quick background. A lot of these informations are already available online, but I just wanted to introduce you. So this Wicking Geotextile is anyone who is working or have worked with geotextiles, so they will understand what is the functions of the geotextiles, essentially separation and reinforcement. The principal advantage of this new wicking geotextile is that in addition to separation and reinforcement, it has a special fiber which is known as hydro or wicking fiber, which enhances the lateral drainage. And means you might say, okay, the traditional geotextiles also enhances drainage, but the difference here is like traditional geotextiles mostly drains due with in gravitational flow. But this geotextile, because of the microfibers, are able to facilitate flow by capillary suction. So that essentially helps us to use this geotextile for pavements or subgrades or bases for removing more water even when the water or the suction is really less or really high, or essentially it's more on the dry side of the optimum. So here you can see some of the schematics. So these are essentially 4-digit groups. So these are the groups, small groups on the surface, and this essentially helps to build the suction force to facilitate the capillary action. And these are some other pictures, and some of them are from the website, so you can find a lot of those images from there. So with that, I will directly jump into my current focus, which is like I wanted to show our efforts in Texas and Minnesota. So the first one is our problems in expansive soils in Texas. So when we say Texas, the one challenge or the one principal problem that we all talk about is the expansive soils. So the principal challenge in this expansive soil, which causes the failure in the pavement, are the soil and shrink behavior, which results in a differential heaving. And because of that behavior, it causes a lot of pavement damage, essentially cracking, rutting, and depression. And this affects the long-term payment performance, causing it to like increase the expenditure and maintenance cost. So these are some of the like the actual field images. So this is basically the, if you see on the right hand side, this is one of the test sites or the region where our pavement test section was constructed. So this region is like the pavements, you can see there are lots of patchwork. So this is the this was a regular activity for the DOT to come and maintain the patch. But again, because of this behavior of the soil, like drying and cracking and shrinking. So because of that, there is a constant damage to the pavement subgrade, and which essentially propagates to the top of the pavement. And that's what one of the reasons we wanted to address, one of the challenges we wanted to address using this geotextile. And on the left-hand side, you can see the failed slope. That is again another principal challenge with the expansive soils. So these are some of the traditional or the most common challenges in the expansive soil or any regions in the world, and especially in Central Texas. So our goal using this geotextile in Texas was to evaluate the feasibility of this geotextile for improving drainage as well as enhance the strength of the pavement layers. So for that, we like as we talked, we have both from laboratory to practice. So essentially, we studied both lab in the laboratory as well as we had field test sections. And I will show you both like how we studied the works in laboratory as well as in the field. So this is, we started with a small laboratory test. So these are very small laboratory tests where we just wanted to check whether this geotextile is able to drain the water. So we did some control box as well as the reinforced box. So once we set up this box and then we studied the drainability or the transmissibility of the Wicking geotextile, we noted like in absence of geotextiles, the volumetric moisture content is much higher. Once we put the geotextile, the drainability or the transmissibility increases, and in the given control condition, it can drain moisture in the lateral direction. And that is something which we are always trying to understand whether it can drain moisture or not. And after we have understood in a small scale laboratory test, then we started to move into some bigger scale or some large scale test. So this was a large scale laboratory test that we did. So this on the left hand side, you can see this is a conceptual model. And on the right hand side, it is the representation of the model that we did. It doesn't look exactly the same, but this had essentially the same function as the what we initially assumed. So we created this box which had different sensors. Essentially, it has moisture sensors, it has shape and accelerometer or deformation sensors, and then we can control the drainage in this box. So this is the large scale test box that we did for understanding the behavior in more controlled manner. And this is some of the steps. So we constructed the box. Like you can see, we collected the soil from the local region, and we essentially constructed the box replicating the pavement sections. Like we had a subgrade of 18 inches, and then we had a base of approximately 15 inches or 12 inches. And then we constructed the pavement. So we have different layers. You can see this is compacting the subgrade and then layers, and then we have this sensor. So these are just the location where we install the sensors, and this is the final test box. And after constructing the sections, we also did perform some quality check. We use the dynamic cone penetrometer, which is Panda DCP, which is also known as variable energy DCP. So we use that to check the uniformity of the constructor sections. And for the reinforced section, we have to do this DCP test separately, once for the subgrade and once for the base, because the DCPs cannot penetrate through the geotextile, and that gives you wrong results. So that's what we did for the reinforced section. And then this is just a representation of what we looked or understood using this big box test. So again, just to see like just a very similar result what we saw in the small test, like the wicking fiber, they definitely helped in enhancing the drainage performance. And I didn't show the control test section results here, but it was able to drain more than the control sections. And another important thing that we noted is like the base layer has a higher drainage than the subgrade layer. The principal reason is that because the geotextiles were essentially on the interface, and the drainage from the base layer is by both gravity as well as capillary suction. And additionally, the grain size distribution of the base layers are much more or bigger than the wicking fiber. So that's why the capillary suction generated in the wicking fibers is much higher than the pore size in the base materials. So it was much quickly, or it was able to drain the base material much quickly as compared to the subgrade. And in the subgrade layer, we saw like it can drain up to 12 inches below the geotextile layer, which was substantial, because if you think it like that, if you can drain the moisture until 12 inches below the subgrades, then you are essentially increasing the stiffness of that layer. And once you are increasing the stiffness, you are essentially trying to improve the long-term performance. So once the traffic loads are there, it will not undergo damages. So that's why, because uh, drainage capacity, there is additional improvement of stiffness along with the traditional geosynthetic that reinforcement capacity. So these are the advantages that we noted from the laboratory studies. And once we were confident, like, okay, this works in the laboratory, then we also parallelly constructed our field test section. So I will now go into what we did in the field. So this is our field, what we did in the field, and this is the project location. So this is located in Texas, this test section. So you can see on the left-hand side, this is the map, which clearly indicates the frequency of expansive soils in Texas. And the red regions are the regions where you will encounter expansive soil every place. So that is one of the principal challenges for the state DOT. And we selected one of those sites, which is Farm to Market Road 1807 in Central Texas or Venice, Texas. And this is what you can see on the right. So this was in 2017. We were doing the reconnaissance of this region and how this pavement looks like. And then we decided with the DOT that we will use the eastbound lane as the test section, and the left and the westbound lane will be used as the control section. And the westbound lane has different asphalt thickness, so it has asphalt layer of around 4 to 6 inches, but we decided to use thinner asphalt, as well as after talking with the DOT, we thought like TxDOT has a huge pile of recycled material, so which is known as RAP material, recycled asphalt pavement. So anyone who is familiar with recycled material, so recycled asphalt essentially obtained from the pavement surface, And the TexDOT Venus, that region, Johnson County, they had a large stockpile. So we thought we will use a marginal material as a base material, which is RAP, and we will use the geotextile, which is like H2RI, to reinforce the RAP material. And at the same time, we will reduce the thickness of the asphalt layer. So we were trying to target multiple things through this test section. And then we thought of comparing our performance with a traditional FB. FB is nothing of flakes base. It is like colloquial in Texas, but it's essentially crushed stone aggregates. So this is what we tried to do, and we constructed 130 feet sections each for both geotextiles with wrap as well as the flex base material. And this is the outline, or this is the schematic of the test section. So this was what we initially thought we will do. Like we will have this base material, and then on the left hand side, you can see that is approximately 15-inch of wrap or reclaimed asphalt pavement material base and 2-inch of asphalt concrete. And we did install a number of sensors. So we had SAA. SAA is nothing but shape array accelerometer sensors, which is the deformation sensors. And then we had earth pressure cells. And in this figure, you are not able to see, but we are able to install at least 9 moisture sensors to monitor the moisture migration within the pavement layers. And then we also did the same for the control set or the test section 2, which is the flex base section. And just to tell you, remember that our control section is on the westbound lane, which is again constructed with thicker asphalt layer and some old traditional flex base material. So that was our control section. And we initially thought we will have this the one of the challenges with this wicking geotextile was like we need to ensure like the geotextile was exposed to the surface, because that is how it will absorb or it will create the capillary suction region. But during construction, it never happens what you plan. So in during construction, what we had to actually do is like we had to cover this exposed region with some wrap material, because a text dot was the text dot was concerned, like if we leave it exposed, someone might damage the geotextile. So that's why in the real construction, we had to cover these exposed regions with wrap material. But surprisingly, that didn't affect our performance a lot, and we still got the desirable behavior. And then this is some of the construction stages that we did. So we had the initial milling and excavation, and then we did this instrumentation trenches for putting the deformation sensor. And then this is the construction you can see on the right, like the construction of the wrap sections and preparing of the flex base section. And then we leveled it. And this final construction is basically done after 7 days. So for 7 days after this leveling, we left the pavement open for traffic, and then we came back and did the surface course. So after that, we also performed different performance monitoring studies. So one of the studies that we did was automated plate load test with the support of Ingenious Geotechnics. So this is a dynamic plate load test. So this is very similar to the resilient modelers, the ASTO T307 studies that we do in the laboratory, but this is more on a large scale. It is a little bit different from the FWD because this applies rapid load or for increasing number of load cycles, and it monitors the deformation. So this is the thing that gives you the field resilient moduli, and we perform this study on this constructed test section. We also did the traditional falling weight deflectometer test. This is just one test showing, but we did actually for over the next 4 years, we did a falling weight deflectometer test over different seasons to understand the behavior of the pavement layers at different times of the region. And you can again see this is like this has a weight hammer of 90 pounds, and this has 7 sensors, and these sensors record the deformations, and it essentially works on the principles of linear elastic theory, and it helps us to predict the performance of the surface layer, base layer, as well as the subgrade layer. So we were able to perform these sections test for all the test as well as the control sections. Now, to quickly give you some results that we have obtained in this work. So what we saw is like in the test section, like which is the reinforced section, the wicking geotextile, you can see this bottom one, this is the green and the red one, those are the reinforced section, and the control section was the other side, which is having no geotextile. We saw the moisture in the wicking geotextile was much lower, and it was this peaks at the period where there was rainfall, and it was able to drain the moisture rapidly after the rainfall, whereas in the control section it stayed persistently high. And another thing that we noted, like the moisture in the wrap section or reclaimed asphalt pavement layer section was generally higher than the one in the flex base section. The reason for that is because the wrap materials are having much finer particles as compared to the flex base. And because of those finer particles, the drainability of the wrap layers are much lower as compared to the flex base. So that was one of the reasons why we thought this wrap material has or retaining more moisture than the flex base material. But in general, both the sections were retaining lower moisture as compared to the control section. And then this is just represented the moisture contour. So we were able to see like the moisture reduces near the edges, mostly in the Wicking Geotextile region. And that is essentially showing like it is draining from the lateral direction, as that was what we were expecting. And we also saw plotting some of the moisture contours. Yes, that was what it was. And we are happy with the performance. Then this is a result from the APLT test. So this is a resilient moduli. Again, I just wanted to mention that this is a composite resilient moduli. And I just want to focus you on the red region because we had multiple test sections in that, but our concern for this presentation is only test section 1 and test section 2 and the control section. What we noted from this APLT test is like the H2RI and RAP section that yielded highest composite resilient moduli. And that like that was interesting observation because we thought the flex base will have higher resilient moduli. But once we went back and checked the various literature, we saw wrap material. The principal problems with wrap material is that they have the lateral spreading, so they are not resistance to lateral spreading. But if you just test the resilient moduli for the wrap material, they have higher resilient moduli individually. So that's why they, because of those like asphalt particles, they are sticking, holding the materials together, they generate higher MR. So that's why the wrap materials essentially generated higher resilient moduli as compared to the traditional flex-based materials for this case also. And then quickly showing you what we saw as a for AWA test results. So this, what we generated from this test was essentially back calculated moduli and rut life. And again, this kind of echoed the same behavior that we were seeing from the APLT. So the wrap layer was showing higher rut life or higher remaining life and higher moduli value as compared to the traditional flex base. And from FWD, it is always difficult to exactly predict the subgrade modulus and the base modulus, but what we did was like essentially for the wrap material, we back calculated the base moduli to be 45 KSI, and whereas for the test section 2, it was almost 25 KSI. And interesting to note, like if you see the control section, which has a thicker asphalt layer, the performance of the base and the subgrade moduli was almost similar, which means the geotextiles along with the drainage was able to replicate the performance of a thicker asphalt pavement layer. So this essentially helps us to verify like if we are able to replace those thick asphalt with a base material which is marginal quality, and then we reinforce it with some kind of geosynthetic, then we can have a similar design life or even better design life. So this was one of the major learnings that we understood from the studies in Texas. So this is what we did in Texas. And once we are confident in this thing, then we extended our work to a different region. So now we worked closely with the Michigan State and Minnesota MN roads, and then we tried to study the behavior of this Wicking geotextiles in this region. Again, the previously few people have studied this work in Alaska, but the challenges in Minnesota was different because it is a different region than Alaska, and we try to address that challenge through our study. So this is what like the general background why we needed to do that work. So if you see on the bottom, I will start here. So Minnesota is somewhere located here. So this is the region which is in the wet freeze region, in north of the American region, and is a wet freeze region. And the challenges when the wet freeze region is like it can develop longitudinal frost cracks, and then there is the local regions of frost boils, And then one of the another challenge is because during the winter, the water enters into this base and subgrade, and the ice expands. And in the spring, when the water thaws away, it is the most weakest. It makes the subgrade really weak. So that essentially damages the pavements in the spring region or when the thaw is happening. So our goal here was these are the three conditions which causes frost heave, which is the freezing temperature, presence of the frost susceptible soil, and the water supply. So our goal was here to cut down the water supply to the layers, or if or maybe potentially remove the water supply, reduce the water supply. So that will essentially help in improving the pavement performance. So with that, we did again set up objective like to again to evaluate the short term and long term benefits of a Wicking geotextile used in pavement foundation for this Minnesota region. So again, we did, before going to the field, we did laboratory studies. So in this one, we did two types of laboratory studies. One was accelerated laboratory loading test, and the other one was the accelerated laboratory drainage test. So the loading test that was performed with Michigan State University and NGOs in their laboratory. And you can see this is the schematic of the test section that is constructed in laboratory. So you can see on the left-hand side, this is the control section, and on the right-hand side, this is the Wicking geotextile section. And then this is again the plan view. So these test boxes were having different kind of sensors. Again, it had moisture sensors, thermocouples, and then there at top of it, there is a loading plate. So this loading plate essentially was used to replicate the field test, so field rapid loading, or it was essentially used to calculate the stresses at different temperature, or when there is a freezing happening in the base, subbase, or subgrade layer, and how this repeated load is going to affect the moduli. So you can see there's a PVC pipes at the bottom, and there was some granular layer. So the water was used to push from the PVC pipes from the bottom. So in this particular study, we approached it like through open system. So we ensured like it is covered with some kind of foam board on every side so that our freezing doesn't occur from the side. And we created a kind of freezing board. So we had a freezing board on the top, and we tried to freeze the soil layer from top to bottom, which is essentially how it happens naturally. So it doesn't freeze from every direction, it happens from top to bottom. So we tried to replicate that in the field. And this is again the top view of the geotextiles. So this is the control section, and this is the Wicking geotextile section. And this is again the different steps of the construction. And you can see the layers are being compacted, and then 2% slope, and the installation of the geotextile and non-woven geotextile, and the control and the slope angle. And on the right hand side, you can see this is the final test setup. And you can see the water tank, which is kind of pushing water from the lower side. So the water we were concerned is moving only through capillary action. And then we are trying to insulate it from every direction using wood and foam boards. And then you can see in the here we have the small loading frame. And finally, in the front, you can see the two boxes. Essentially, the Wicking geotextile is extended into these boxes, which was used to collect the water that is coming in. And also, I think we also extended this to some kind of rainfall studies, but I have not included that in this presentation. But mostly, I just wanted to show how the freezing affected the performance. And then the next study that we did in laboratory was again like the accelerated laboratory drainage test. So this one was performed at Texas A&M. So in this one, we again have two test sections. One is for the control, another is from the reinforced section. And we again tried to insulate this section with geofoams on all the sides because we wanted to ensure that we have a top-down freezing. And the advantage we had that we had a big environmental chamber, which we were able to set at minus 18 degrees Celsius, and we can push this entire box. So this is approximately 3 feet by 3 feet box that we were constructed using these three layers like subgrade, base, and subbase and base layers. And we had a water supply, and we were able to push this entire setup in that environmental chamber. And this is again for the control. And you can see on the reinforced, we again have these two reinforcement strips, and we are able to collect the moisture coming out from the reinforced or the geotextiles in a separate container. So This is again different steps of construction. So we had different sensors installed in this box also, like we had deformation sensors, we shape array sensors, then we had moisture sensors, and then we have thermocouples. And you can see on the right hand side, these are the two final test setups. So the top one is the control section without geotextile, and the bottom one is the one with geotextile. So this is a 3 feet by 3 feet box, and again, this you can see we were able, if you can see the small white structures on left hand side, those are the actually big environmental chambers, and we were able to push this entire box or keep this entire test setup in an environmental chamber to understand the drainage behavior when it's freezing or it's thawing during that period. So these are the two laboratory tests that we did for this new region study. And again, I just wanted to quickly show you some results, but there are a lot of more results. I just wanted to show you some main highlights. So the first one is on left hand side. What we saw is like the moisture, like a subgrade. In this is from the accelerated loading test, which was performed with the help of NGOs and Michigan State. And we saw that again, as compared to the wicking section, the control section or subgrade had higher moisture, and it was mostly during thawing, because what happens is like during the freezing in the open system, the ice lenses expands and that creates more voids. And since we are continuously supplying water even during the test, that pushes more water within the system, and that causes more thawing water or drainage of more water during the thawing. In case of wicking geotextile, that wicking geotextile are able to drain that excess water even during the freezing period. So that's why it didn't have enough water, or it didn't show enough increase in water as compared to the control subgrade. And again, one another thing that we saw is again like in case of the Wicking geotextile, interestingly, we saw it was freezing quickly as compared to the control. The principal reason that we understand is because there is some interface gaps or some interface layers, and the freezing was happening through that. So that's why the freezing noted in the or the force penetration in the wicking geotextile sections was much higher as compared to the control section. And during the loading test, this is something which really interesting. So we tried to calculate the permanent deformation and resilient moduli in that accelerated loading test. And what we saw, like if you see on this one, the I think I would like to, this is really interesting way of showing how the performance varies. So this is showed in terms of probability of permanent deformation less than a particular value. So what we saw, like this reinforced section, they can have a chance of getting higher deformation of up to 0.32 inches or 0.31 inches. Whereas the wicking geotextiles, they have a maximum chance of getting a deformation of up to until only 0.28 inches. So definitely they are having less deformation. And also the probability of getting any particular deformation or less than that particular value was much higher. Probability of reaching a particular value of less than particular value is much higher in wicking geotextile as compared to the control section. Similarly, the values of the resilient moduli, it shows like chances of this layer or in particular layer, like for example, if in this case it's showing 13,000, the chances that the wicking geotextile will have a resilient moduli of less than 13,000 is much lower as compared to the control section of the unreinforced section. So by this accelerated load test after freezing temperature, we saw like, yes, this geotextile is also effective in the laboratory for different freezing or the freezing and the thawing cycles. And then this is again the results from the drainage test. So in the drainage test that we saw like during the freezing, so this is how the freezing front moved. So this was essentially monitored with the help of different sensors, like I mentioned, like thermocouples, moisture sensors. And we saw like the subgrade was not freezing properly, but the base and the subbase was frozen completely. And we stopped the test after that. And this is again on the right hand side. So there are lots of graphs. So this is a temporal variation of the moisture content. So you can see like this is the representation of like the different moisture content for front and back and for big control and reinforced section. And we saw like this is for the reinforced section. In general, the moisture in the reinforced section was much lower as compared to the control section. So again, from the drainage test also, we saw that this is very few representative images, but if you need more information, please feel to reach out to me and I can provide you more details on this. And parallelly, like again, since we were again thinking of going actual field studies, so this project, we did have a field study. So this was performed in Minnesota, and it was performed with the help of the MN roads, and it was constructed on westbound I-94. So they have different test cells. So our test cell was cell 2228 and 2229. And it's on a westbound lane, and we constructed that in 2022. So we have the one control section and we have one reinforced section there. And this is again the schematic of the control and the reinforced section. So you can see we had a subgrade, we have 12-inch subbase and base. And then we have these different kinds of lanes and our sensors which were installed at that region. So we had moisture sensor, we had thermocouple tree, and then we also had a deformation sensor. So which we installed at different regions in that uh, field region in I-94 in Minnesota, and we were constantly monitoring, we still monitoring the performance of this project. And then these are some of the representative images, like how the construction was happening. So this is entirely the pavement of the Wicking Geotextile info section. So again, the challenge what we faced here was how to ensure drainage on the beyond the pavement layers, because since this being an interstate, we were not able to extend this geotextile into some or expose it to the surrounding regions. So what like the construction engineers came up with a solution, like we will create a trench there and we will push the geotextile in the trench, and then we will cover the trench with some coarse aggregates. So by that we will ensure like this geotextile is not exposed, and again it also ensures the performance. And then we also did multiple control tests, like we did the DCP test, then the nuclear density gauges, and then we also were able to perform LWD tests with the help of University of Texas at El Paso. And then we are also doing some of these ongoing works, which is essentially falling weight deflectometer as well as GPR scans. So this is still an active project, and I think this still we are getting the results and trying to analyze this performance. Just to give a quick overview on the results, what we saw that. So this is the results from the moisture content. I will just focus on the subbase moisture content as of now. So what we see, like in control section, the drainage was slower and as compared to the reinforced section. And in Wicking Geotextile section, you can see like the drainage was quite rapid, because that's what one of the activities. So the advantages of Wicking Geotextile. And in this one, I have not shown that because this is like little bit old result, but in general, during the construction, what we had was like during construction of the control section, there was no rainfall, but during the construction of the reinforced section, there was rainfall. So that's why the subgrade was already on the higher moisture content for the Wicking geotextile, which is evident here. But over the longer period, because of the geotextile, the subgrade moisture is continuously going down. So the Wicking geotextile is continuously draining the moisture, and the moisture has now gone down below the base, below the control section. So that is definitely one of the advantages that we are seeing because of the geotextile. And this is again, we are just showing one representative sample, but this is a general trend for both center as well as the edge of the pavements. And then some of the analysis from the metric potential of the suction sensors. So one of the things that we noted, like the metric potential jumped during sub-freezing. As the freezing started, you can see here the temperature went down, the material or the subbase froze, and the capillary suction went significantly high. So that resulted in maximum increase of the metric potential. And like during the thawing period, the comparison again, because everything doesn't go as planned for the field construction. So the comparison between the cells was not possible because the metric potential was not recording the data during the thawing season, because it was really saturated and the potential sensor stopped recording the data. But during the freezing season, it really showed up like the formation of the ice, or the beginning of the ice formation, and how our performance. And then finally, the permanent deformation using the shape array. So in this one, we just wanted to show the deformation below the pavement or the wheel path, and we saw like as compared to the, you can see here, like the control section, which has much higher deformation as compared to the test section or the reinforced section. And this is like shows like both like from the reinforcement action as well as from the drainage action, the reinforced sections are having much better performance as compared to the control section. And with that, I will just quickly show you some of the ongoing efforts because we are still learning a lot on this thing. So what we are trying to do right now is now trying to see how this geotextiles is effective in the slope. So this is the work which is ongoing by one of the my colleagues, Avinash. So he's working on this one right now, and I appreciate him for sharing this information. So he is trying to use how this geotextile can be helped for reinforcing the slope, because again, geotextiles have been used for reinforcement, but those are traditional. But this geotextile do have an advantage of like moisture removal. So he is doing lots of direct shear testing and interface testing. And this is the schematic of a large box, which is again trying to construct. And we will do a full scale test of using this geotextile, understanding how it helps in improving the slope stability of pavements under wetting and drying, as well as freezing and thawing. And another thing that we really wanted to focus on, because most of this geotextiles application is often challenged because of the cost. So we are trying to address that one by performing some life cycle analysis. So this is some preliminary data or studies that we tried to do earlier, like it was based on the cradle to gate and transformation site approach. And this is still ongoing. There are lots of data which we are still trying to gather. We are trying to use OpenLCA for performing this analysis. And this is still ongoing work, and I believe we will have some more data to share in the next year or something. So with that, I will just try to summarize and close this the discussion, like what we have learned or I have learned so far as a part of this project over the past 6 to 7 years is like definitely this geotextile was found to be effective in improving the performance both in Texas as well as in currently we are seeing the improvement in Minnesota, and we're still monitoring that. And the advantages of this geotextile is like in addition to reinforcements and separation, it can also ensure lateral drainage. And then we did those or verified some of these things in the laboratory, and we are doing some long-term monitoring like we did. We are still trying to do some monitoring for the Texas pavements, as definitely we are having a lot of monitoring done at the Minnesota I-94. And definitely one of the final thing is like we need to have some sustainability benefit analysis or life cycle analysis even before we can have a long-term benefits or show it as a sustainable product in the future. So with that, I think I will thank everyone for your time for attending the presentation, and I would be happy to answer a few questions. Over to you, Nitin.
Thanks, Dr. Vishwas, for a nice presentation. Actually, it reminds me my PhD days when I was using a geotextile for controlling the expansive soil, but the conventional geotextile. And knowing this Wicking geotextile and how effectively it is working, it is a really must have enriched with your knowledge and how the laboratory results are transformed to the field results and considering all the durability aspects. So I'm really glad. Before we go to the Q&A session, Dr. Sen have one announcement for the next webinar. So Dr. Sen, can you announce and then we can go for the Q&A?
Sure. First of all, thank you so much, Dr. Biswas. That was a wonderful presentation. I thoroughly enjoyed it. Yeah, really, thank you so much for taking the time to do this for our seminar series. I had one quick announcement about the next seminar. It's scheduled for December 4th at 9 a.m. The speaker is Dr. Julia Marasco. She's a postdoc at Lehigh University, and she will be talking to us on innovative developments that are going on in the field of infrastructure assessment using new AI methods. So I look forward to seeing you all on December 4th again for this. Go on, Dr. Tiwari.
Yeah, thanks, Dr. Sen, for sharing. And for everyone, I'm just sharing a event link for the other event so that if you want to register, you can register for that event in a chat. Uh, Dr. Vishwas, we have some questions in chat room. If you can see and if you can answer those questions, that will be great.
I think, yeah.
Starting from 9:45, I guess.
Starting. Okay, my time zone is different. I'm just trying to.
It should be
Okay.
10:45 for you.
Okay. Okay. So first one is, what was the name of the equipment similar to FWD used in Texas? Okay, so that is APLT. That is automated plate load testing. So that is a kind of a dynamic loading device, and it's very similar. The behavior is very similar to the laboratory resilient modular testing, Astro T307. But the loading sequences and the loading and loads are different. Then the next one, how does the wicking geotextile differ from separation and protection geotextile usually used for embankment construction? The permeability of water and stability of the embankment slopes. So that's an interesting question. Actually, this geotextile is having, like, it has the two interlayers. So it has both HDP, high density polyethylene fibers, as well as the wicking fibers. So those fibers are, since this is again woven, so this is really works good for separation action, like the traditional geotextile. And for reinforcement also, this HDP fibers provides the reinforcement. The only advantage here that is really interesting is the wicking fiber, or the white small fibers that provide the layers of drainage. So that's how it can perform all of those performance which can be done by traditional geotextiles, and also provide added benefit of the reinforcement and drainage. I think I can provide you the more link to that. I can provide Dr. Tiwari the link to the product details or other behaviors of geotextiles, but this can perform function as well as the additional drainage function. Yeah. And the next one is, how many geosynthetic layers would you suggest for pavement near the slope to sustain increasing traffic and other environmental load? Considering they might, what is the expected lifetime, and they might clog with fine materials over time. So the first one, like it is totally dependent on like the uh, I cannot say how many exactly you will need, but for slopes the problems will be different, because I am not sure like how you want to apply traffic load on slopes, because the slopes behavior is different. The pavement will be much on the inner side, the traffic will be on the inner side. The reinforcement for the traffic load will be different, and the slope stability reinforcement will be different. And the lifetime, the clogging, there is some good work done by Professor Jihan from Kansas, University of Kansas, KU. They also did some work on this clogging of this geotextile, and they noted like there is some clogging, especially if you are using it in very fine soil. But again, since these wicking fibers are having the pores which is comparable to the clays, that's why those partial cloggings does affect, but it also kind of it balanced by the capillary suction forces developed in the geotextile, because those capillary suction is the thing which essentially drives the moisture in these wicking fibers. So even with partial clogging, they noted like they have a case study which they performed after 2 years of study, I believe, but it still the performance was quite appreciable. So yes, the performance will go down, but still it does perform appreciably. And other than that, propylene. Okay, yeah, thanks, Rene. So yeah, so the fibers are polypropylene. Thank you. Laser particle. Can geotextile be used to prevent liquefaction problems for rapid dissipation of pore pressure during earthquakes? That is kind of interesting thing because this is like based on the capillary suction force. And I don't know if you are, because this excess pore pressure generation during liquefaction is a really quick action force. And I don't know if geotextile will be able to rapidly drain that moisture. Again, I have not done that study, but definitely if you are able to do that and find something that will really be interesting to see. But yeah, I don't know what will be the results in case of the seismic loading for this case. The view and the final that one is the Wicking Geotextile is shown to have lesser vertical deformation in the control section. How can we quantify the improvement factor? Is be repeated. Yeah, so that's again an interesting way that how can we quantify? So that's what I think we were trying to work with the company last year. Like they were trying to come up with a MEPDG guideline, like how to have this moisture drainage. So essentially, we were trying to see how to convert this reduction in moisture to the effective moduli region. So once we have developed an effective moduli around the reinforcement region, that can be taken into the pavement design software and and run a pavement analysis on that. So that is definitely something which we are trying to work and trying to see if how we can extract this drainage water to the MEPDG or align this with the MEPDG guidelines. We tried to work that on that. And I strongly believe I think some of the folks are trying to work on that one. And can this performance be repeated? So far, like we have seen at least like from past studies in Alaska, they did note that Wicking geotextile works in their case. We have seen that in expansive soil, it also works in that region. And right now we are monitoring some performance in Minnesota as well as doing some additional studies on slopes. So yes, as far as our studies are concerned, we can say in our studies, we saw it is working. But again, whether it will work in every case or not, that I am not sure. So yeah, that I think that needs to be more work done, or more case studies need to be done on those cases. And okay, so we have how did you measure the strain of geotextile? What type of sensors? So this is the like what sensor we use was not essentially measuring the strain of the geotextile, but we were measuring the deformation on top of the geotextile. So that's what we are doing using the shape and accelerometer sensors. So they essentially are the continuous sensors. They get the deformation below the pavement, and we were measuring the pavement deformation on top of the subgrade, and we were using that to back calculate the layer moduli. So that's what we were using. So we didn't have any strains to measure the deformation of the geotextiles per se. And what is the other question? Durability of Wicking geotextile. Wicking geotextile work as a I have a question about durability of the Wicking geotextile work as a horizontal drainage layer. Yes, again, that's really interesting question. But most of the time, like what a lot of studies, like geotextiles are generally found to be more durable and like the as compared to other methods. And once I will be happy to share some of the links for this product, and they have long term, like they have the durability checks, like any of the geotextiles, they come with different studies like the UV durability or the strength and tensile, all those things. So according to the manufacturer website, they are durable to different kind of loads. But again, the pavement performance, we are now only monitoring for 2 years, but the pavement design life that we designed was for 20 years. And I think the Minnesota roads are also designed for more than 20 years. So actual durability will only be realized after that time. But right now, at least after 5 to 6 years of construction, the performance is quite good in that regions of Texas at least. And we believe like it's performing appropriately what we are expecting. So far it's durable, that I can say. It worked to the geotextile in non-expensive soils as well. Yes, means definitely like this is like kind of a question that you need to think about, like what are the options you have? Like, is there anything like is there the economical option, or it is a there is some constructability issues or not? If you can see like if it's the economical option and if there is no constructability issues, then definitely it should work with non-expansive soils as well. Yeah. Then yes, there is a one-year style on mice. Okay. Okay. Yeah. So, okay. Thanks, Renee, again. All right. I don't see.
Yeah. Yeah. Thanks, Dr. Vishwas. I think now I allowed all the participants to like they can unmute if they want, and if they want to turn on their cameras, they can do. And if they want to have an informal discussion with Dr. Vishwas for any kind of a collaboration, anything, I think we can have for maybe 2, 4, 5 minutes. If somebody wants to talk to him, that's like the motive of this webinar is one to share the knowledge, second to create a collaborative environment for everyone. So all are feel free to turn on their camera, and if you turn on your camera I can also take one picture which I can use for circulating on LinkedIn and other places. So feel free to do, and if you have any question feel free to ask to Dr. Vishwas directly. So now the camera and like mics are allowed, you can unmute and you can turn on your camera if you want.
There was another question posted by Richard.
Mhm.
Okay. Yeah, I guess we are in the influence factor. Yes, that is something what we were trying to do. Exactly. We were trying to essentially come up with an improvement factor for the, like I mentioned, we did see like the geotextile has a like influencing a region of up to 10 inches in the fine subgrade soil. So essentially that region improvement or the moduli is increasing. So we did back calculate that improvement factor in one of the earlier works, but we're also trying to see how we can include that more in the perspective of the MEPDG. Yes, I think Rene has a question.
Renee, go ahead.
Thank you. That was a wonderful presentation. Thank you so much. So my name is Rene Laprade. I work for Solmax. We're the manufacturer of the product. So for anybody who's not aware why I'm just chiming in here, we're also working on, I guess, very hard right now at incorporating the mechanical and hydraulic stabilization benefits of the product within the pavement ME application. So what we're calling here MEPDG. We have a gentleman on staff who is a PhD on pavements who's been doing months of finite element analysis. So that's, there is certainly a move towards being able to incorporate this moving forward, because as we all know, AASHTO 93 has been a very popular design methodology, but it's still, I find it amazing that a methodology that's basically centered around a couple of data points has gotten so much lifetime over the years. So I didn't want to take over this, but I just so people are aware, there are efforts towards the pavement ME development.
Thank you so much, Rene. Yeah, so actually, I believe Daniel, he was working with us last year, and this year I think he's working on coming up with some MEPDG, finite element-based MEPDG, and I believe he is getting a lot of data from, I think, Missouri, from us, and like Minnesota, and he's trying to come up with this like pavement ME design, which is more focused, moving away from AASHTO 93, because like Rene mentioned, yeah, we want to move away from AASHTO design guidelines to more MEPDG guidelines. Yeah.
Yeah, I think thank Dr. Vishwas. I think we can end this webinar now. So